Alright, hey everybody, my name is Steven Gouner. I am talking about the thermocouple time constant experiment. It might be a little repetitive because I think I might have done the wrong experiment, but I'm just going to go with it. Alright, well, first off, this is what I'm going to talk about. I'm going to talk about our group, everybody's goals and assigned positions. The goals of the experiment, the thermodynamic background for the experiment, the apparatus we use for the experiment, the procedure, the data and uncertainties that go along with the experiment, and then we'll finish up with questions. Alright, a little bit about our group. I'm Steven Gouner, like I said earlier. I am the group leader. Then we have Conrad and James. Conrad is the reporter for our group, and James is actually a Toastmaster for today. Alright, talk about experiment goals. The main goal for this experiment is to record transient response of a thermocouple probe. Basically, we're just going to see what happens when you put a thermocouple into a different type of temperature. We're going to gather the data we get from putting the thermocouple in the waters. We're going to process the data, meaning just kind of look through it and see what we can understand for it and interpret it. And then lastly, well, not lastly, but we're going to present the results graphically. We're going to go ahead and make some Excel charts, and that way it's easier to see what's actually going on in the experiment rather than just seeing a big list of numbers. And lastly, what we're going to do is determine the proper time constant that it takes for the probe to reach its final and initial temperatures depending on what type of water it's in. Alright, just a quick thermodynamic background on thermocouples. In order to find out the time constant, there's a few different things we have to go through. The first thing is to do a transient energy analysis, and we'll use this energy analysis assuming that there is no thermal gradients. This is called the lump capacitance method, and all this is, I mean, we have all seen these, or this formula, at least in heat transfer, but it's just things, you know, density, volume, specific heat, then the time over the temperature, or temperature over time derivative with the heating coefficient, surface area, and then different temperatures. Just the capital T, that is the temperature of, that's actually temperature versus time. The T infinity is temperature of whatever medium the probe is in. And down there at the bottom, T naught is the temperature of the actual probe. And if we integrate that first transient energy analysis of the rate heat is converted and the rate of thermal energy change, we'll get the equation I have listed underneath. And the left side of that is actually a graph, the graph that we're going to be using for the data. Alright, and then the ultimate goal of this experiment was to find the time constant for the temperature to reach its maximum and minimum points to level out. And to do this, we can follow these steps of manipulating the equations. First we do the integration, and then we can find the tau from there, and then from finding tau, we can get the time it takes for it to actually happen. Alright, the apparatus used for this experiment, we'll need a 500 milliliter flask of either boiling water or ice water, depending on which part of the experiment that you did. Hot plate or ice, once again, depending on which type of experiment you did. Paper towels, PDAQ data acquisition capable computer. That's just a software that gathers data from the thermocouple, and an 1/8 inch type K thermocouple. We used a type K thermocouple. From my research, type K thermocouples are they're the cheapest thermocouples to use, and they're the most efficient. They can read a very high range of temperatures. So the difference between type K and other types is the types of metal that's used in them. And a type K thermal conductor, it's chromo and aluminum. And what it is, a thermocouple is it's pretty much a long rod, and at the end of the rod is two metals soldered together. And the way it works is there's a current that's pumped through the rod, and the difference in current between the two can be changed into a temperature. There's formulas and stuff like that. That's how we get the actual temperature from using the thermocouple. All right, the procedure for this experiment. First, it's probably the hardest part of the whole experiment, is to set up the computer program. It's pretty difficult. I didn't go into depth into the steps that can be seen in the lab manual, but it's not too bad. It's just a couple of clicks. It's just a program that not too many people are familiar with. Secondly, after everything's plugged in, we are to insert the thermocouple into the either ice water bath or the water on the hot plate that's boiling. And then what you do is once data is gathering and your thermocouple set in your bath, you just allow it to sit there and gather data. And you just watch the data until it reaches a certain point, depending on if you're in the boiling water or the iced water. You can kind of, I mean, we all know how hot it is, how hot water boils, or how cold water freezes. So we can kind of estimate when the data is going to level out. We can actually see it. The next thing to do is save the data, and then after that, we'll do all the calculations and figure out all the things that we need to know from that. All right, the predicted data. Once the thermocouple is placed into the water, it's predicted that the temperature will linearly increase or decrease depending on which bath you insert the thermocouple in. It's not exactly linear, but it's close enough to where we can just call it linear. It's a good estimate. And then once the thermocouple is taken out of the bath, it will then go back down to its steady state. So that's assumed because it'll just go back to room temperature. And also uncertainties for this experiment specifically. Room temperature is an uncertainty. It's taken account for in the formulas. But if your room temperature changes from the time you start the experiment, and between the time you start it and the time you finish it, it can kind of skew your data a little bit. So you just got to be careful with that. All right, is there any questions? And those are my references.